take a look at your warm-up questions. And for the first part, we're going to do just in the chat. We don't need to switch to a document camera. And we want to assign oxidation numbers or oxidation states on sulfur for each of these compounds that were given. So in the chat, for A, what would the oxidation states on sulfur be? Make sure you put a sign in there too. What would the oxidation state on sulfur be in H2S? -2. Good. We know that hydrogen is a +1. So +1 times 2 gives us a +2. We know the sum of the oxidation states has to be 0. So sulfur is going to be a -2 for its oxidation number. All right. How about B? What would our oxidation state on sulfur be? Good. It's a free element. Okay. It's not in combination with other elements in a molecule. So it's going to have an oxidation state or an oxidation number of 0. Okay. How about C? +6. I agree. Okay. We want to put the plus and the minus in there so we know. We know hydrogen is a +1 and there are 2 of them. So that's a +2. We know oxygen is a -2, so that gives us a -8. -8 and +2 gives us a -6. We know the sum has to be 0, so sulfur is a +6. Good. All right, how about D? We're looking at a sulfide ion. What's the oxidation number? Good, -2. It's a monatomic ion. The charge on the monatomic ion is the oxidation number. Excellent. Okay, how about HS-? Actually, it is 0, isn't it? Hydrogen's +1. It is. You're right. Hydrogen is +1. The sum is -1. No, it's not. It's not 0. Hydrogen's +1. We want the sum to be -1. Yeah, it's -2, right? +1 -2 gives us a -1. Okay. How about sulfur dioxide? Good. Oxygen's a -2. -2 times 4 gives us, or -2 times 2 gives us 4. -4. So sulfur has to be +4. Good. How about sulfur trioxide? +6. Good. -2 times 3, that gives us a -6. -6 plus 6 gives us 0. Excellent. Everybody feel good with how we assign oxidation numbers? All right, excellent. So let's look at this redox reaction, and we want to balance it in an acidic solution. Okay, so I'm going to switch over to my document camera. I just forgot what I'm doing. Here we go. All right, so here we go. And I actually don't have it done yet. We're going to do it kind of together because oftentimes when it's already done, it's hard to kind of see what you did in each of the steps. So if we look here, the oxygen here is changing its oxidation state. It's going from a -2, actually this is a -1 because it's peroxide, -1 to a 0. Okay, so we'll write that. We've got H2O2 yields O2. And then our chromate is also changing. So I'm going to put that down just a little bit. So we've got, we'll put it here. So we've got Cr2O7, 2- goes to Cr +3. So our first step is going to be to separate our 2 half reactions. Let me see if I can get that a little bit clearer. That's the autofocus. See if that helps a little bit. Okay, so now we're going to look here. We're going from a -1 to a 0. So oxygen is being oxidized. Okay. We don't have anything other than hydrogen or oxygen, so we don't have to apply the first step here. We're going to balance our oxygens by adding water. We've got 2 oxygens here and 2 oxygens here, so we don't have to add water in. Now we're going to balance hydrogens by adding hydrogen ions. We have 2 hydrogens here, so we need to add 2 hydrogen ions here. Now we need to balance charge. We've got a 0 charge here. We've got a 0 and a +2 charge here. So we're going to add 2 electrons in order to balance out that half reaction. Now let's look at the dichromate. Okay, first step, 1 or 2 chromiums here, 1 chromium here. We have to balance the chromiums. Okay, now we have 7 oxygens here. We're going to have to add 7 waters here to balance out the oxygens. And we can do that because this is taking place in an aqueous solution. We can add water in. Now we want to balance the hydrogens. We've got 14 hydrogens here. We're going to add 14 hydrogen ions here. And we can do that because it told us it was an acidic solution. Okay, for charge, we have a +14 and a -2 on the reactant side. I'm going to write it down here. That gives us a +12 on the reactant side. And we've got 2 times 3, we've got a +6 on the product side. I don't know why that middle section is not very clear. So to make the charge equal, we're going to have to add 6 electrons to our reduction half reaction. Oops, that eraser doesn't work. Okay, everybody good so far? Again, we're kind of following.
Could you explain it from the beginning again? The screen froze in the beginning of the equation when you were showing it.
So up here?
From the second part.
Okay, so we want to balance the chromiums first. Okay, so we're going to put a 2 here. We want to balance the oxygen second, so we're going to put 7 waters here. We're going to balance the hydrogens by putting 14 hydrogens here. And we're going to balance the charge by putting a -6, because we've got a -6 and a +14. That's going to give us a +8. -2, that gives us a +6 on this side. And we've got 2 times 3 +6 on this side. Good?
Yes, thank you.
You're welcome. All right, now, next thing. Electrons gained in the reduction have to equal the electrons lost in the oxidation. And if they're not, we have to multiply the half reactions by something to get them to be equal. So in this case, if we've got 6 electrons being gained, we need 6 electrons being lost. We only have 2 electrons being lost. So we're going to multiply this half reaction by 3. Okay, so that's going to make this a 3, a 3. This becomes a 6, and this becomes a 6. Okay, now electrons gained equal electrons lost. That's always going to happen that way. Okay, we've got 3 hydrogen peroxide. Okay, we've got 14 hydrogens here, and we've got 6 hydrogens here. So these 6 hydrogens are going to cancel out. 6 of the 14 hydrogens are going to cancel out here. So that's going to give us 8 hydrogens net. Plus dichromate. And then on the product side, we've got 3 oxygens plus 2 chromiums plus 7 waters. And then we can check and make sure that it's balanced. We've got 6 hydrogens here plus 8 hydrogens here. That's going to give us 14 hydrogens on the reactant side. 7 times 2, that's 14 hydrogens on the product side. We've got 6 oxygens here plus 7 oxygens here. That gives us 13 oxygens. We've got 6 oxygens here and 7 oxygens here. So that's 13 oxygens. We've got 2 chromiums here, 2 chromiums here. So our atoms are balanced. Okay, we've got a 0 charge here, a +8 charge here, and a -2 charge here. That's going to give us a +6 on the reactant side. We've got a 0 here, 2 times +3, a +6 and a 0. So my charge is balanced. So that's my balanced equation. How do we do? Everybody okay with balancing redox reactions? Okay, there was a question here for signing oxidation numbers. What would you do if you had something like, okay, so you wouldn't have, so the question from before, Stephanie, you asked about H2SO4 2. That's not a compound because the charge on hydrogen is a +1. So you wouldn't have that 2 after the sulfate in that compound. That doesn't exist, what you have written there. Does that make sense? Now, the question, another question said, where did this number come from? Okay, so if we go back up, okay, we had 6 hydrogens here in our oxidation half reaction, and we have 14 hydrogens here in our reduction half reaction. We're not going to put 14 H+ on this side and 6 H+ on this side. You're never going to have the same thing on both sides of your equation. Okay, the net would be these 6 cancel out, and 6 out of the 14 cancels out, and that's where that 8 comes from. So this is the net number of hydrogens based on here and here. Okay, everybody good? Oh, we have a question again. Okay, so Stephanie, you asked about how would we do something like this? Okay, the charge on hydrogen is a 1 and the charge on sulfate is a -2. So when we write the formula, it's just going to be this. This doesn't exist. Okay, I think what you might mean, let me see if I can come up with something different. What if we have, let's do this. Nope, that's wrong. Okay, how about something like that instead? Okay, since this doesn't exist. So how would we find the sulfur in this? Okay, so how would we do that? Well, there's a couple of ways we could do it. What I would do is just look at the sulfate. Okay, the charge on the sulfate's a -2. And then we know that oxygen is a -2. That gives us a -8. The sum has to be -1, so oxygen has to be +6. Okay, so +6 -8 gives us -2. This whole thing becomes -2. And there are 3 of them. That gives us a -6. Aluminum is a +3. That gives us a +6. So the whole compound is 0. Oh, geez, do we have storms going on? Oh, sorry. If you have storms, that's not good. All right, well, we'll do the best we can. And I am recording. So if you do drop out because of storms, oh yeah, it's nuts. Oh, geez. I'm actually on Long Island at my parents' house. There's no storm here right now. Oh boy. So if we have any kind of issues, I am recording it. It'll be on Canvas later on tonight. All right, my friends. So let's go back. We're going to do 2 quick review problems for tomorrow's test. Very similar to what we did yesterday. Okay. Actually, I just kind of changed the numbers in a way. All right, so here's our first one. We have a titration. Okay, it's a strong acid, strong base titration. Calculate what your pH is at each of the points in that titration. And hopefully, since we did a problem like this yesterday as a review, when we do a problem today, you'll be in good shape.
Do we write the equation out as LiOH plus HCl into the products, or can we write it out as OH plus H plus into H2O?
Yes, don't include the lithium and don't include the chloride because they're spectators. So yeah, just hydrogen
Okay.
plus hydroxide. Yep.
Got it. Thank you.
It's not really going to make a difference in your calculations, but it's not really accurate to what the reaction is.
And should we do that with any titration problem like this?
Any titration problem that's a strong acid, strong base is just hydrogen plus hydroxide. Yep. Agreed.
Okay.
All right, so I'm going to switch over to my document camera and let's see how you did. So get rid of that too. Okay. All right, let's see how you did. Piece of paper. All right, so let's look at the first one. All right, so when we take a look at the first one, okay, first we have our reaction. So we have the hydrogen from the acid reacting with the hydroxide from the base to produce water. And yeah, we don't want to include the spectator ions. So the lithium and the chloride are not included. Since these are in two different solutions, we're going to take the molarity times the volume for the acid and figure out how many moles of acid we have. We're going to take the molarity times the volume for the base and find out how many moles of base we have. And then it's a limiting reactant problem. We have less hydroxide than we have hydrogen ion. So all of the hydroxide is consumed. Some of the hydrogen is consumed and some of it's left over. We can calculate the pH from the hydrogen that's left over, except that this is moles and we need molarity. So we would take the moles of hydrogen left unreacted, divide it by the total volume. That'll give us our molarity. And then take the negative log of that, and that'll give us the pH. So 1.478 is the pH at the first point in our titration. Okay, questions on that so far? All right, now the second part, same reaction, hydrogen reacting with hydroxide to produce water. We're taking the molarity times the volume, that gives us the moles of acid. Molarity times the volume, that gives us the moles of base. We're at the equivalence point. The equivalence point is when the moles of acid equal the moles of base. So all we have in the solution is pure water. In pure water, the hydrogen ion concentration equals the hydroxide ion concentration. The pH is going to be 7. All right, so let's look at the last one. Okay, same reaction. We're taking the, well, actually, we already know this. We calculated this a couple times. The molarity times the volume for the base. Now the base is in excess. All of the acids consumed. We have the moles of base that are in excess. We need to calculate the concentration. This is the total volume. Okay, 50 plus 100. Okay, I think that's what it was. So we get our molarity. We can calculate the POH, since this is hydroxide, subtract it from 14, and we can figure out our pH. Okay, strong acid, strong base, all good? All right, so let's go back. And let's do one other titration. Again, you've done problems like this. You've done homework on this. We've done several different examples. So here's one last titration. Okay, this is a weak acid with a strong base. Okay, the first step, we want to calculate the pH of just the acid solution by itself before we start adding the base. So let's do that part first. And you can use yesterday as an example. This isn't exactly the same problem. I actually switched it. But you can use that as a model if you need to. Oops, sorry. All right, so I'm going to switch to my document camera. And let's see how we did here. We're just doing the first problem. I wouldn't expect that you have it all done. But let's see how you did on the first problem. All right, what if I change this a little bit and see if that'll get rid of whatever that is. There we go. Now the glare's gone. All right, good. Okay, so we have acetic acid. Okay, in an aqueous solution, it's going to donate its hydrogen ion. We're going to produce acetate and hydronium. Okay, this is a weak acid problem. Okay, we make our ice chart. We write our K expression. 1.8 times 10 to the minus 5 equals x squared over 0.200. Again, this x is insignificant, so we're just not going to include it in our math. Multiply by 0.200. Take the square root, that gives us x. X equals the hydronium ion concentration. So if we take the negative log of that, that gives us our pH. So our pH is 2.721. Weak acid pH. We okay with that one? Now, before we do anything, oh, did I just freeze? Do you want me to do that again? Okay, so we have our reaction. We're going to do our ice chart. We're going to write our K expression. We're going to solve for X. X is the hydronium ion. We can calculate the pH of the solution. Better now? You're welcome. All right, now we're going to start our titration. Okay, we're adding hydroxide to our acetic acid. So without any math yet, just write the reaction for the hydroxide and the acetic acid. Let's see if we can get that part. Really, the math is very similar. It's more what's the reaction. So you're adding hydroxide to your acetic acid. What would your reaction be? If you are at, the question is, so in a problem like this, if I'm given a Ka, I need to do an ice chart first. If you're doing just a weak acid or a weak base, you're going to start with your ice chart and your K expression. Okay, here, well, actually, we're going to write an ice chart here too. So yeah, you're really going to write ice charts. Yeah, I probably agree with that. Yeah, they're a little bit different what the ice charts are. We'll look at this one in a second. Okay, so yeah, you would want to write an ice chart anytime you're looking at this. All right, so think about what acids do. Acids donate their proton, okay, to bases. So the hydroxide becomes water. Okay, this is our base, this is our conjugate acid. And the acetic acid becomes the acetate. Okay, so there's our reaction. All right, now, strong acids and strong bases react to completion. So what you need to do now is figure out what the moles of base are and what the moles of acid are. Figure out which is the limiting reactant and what's your excess. Okay, you're going to do that with an ice chart. It's going to be moles instead of molarity like we did in our first one. And it's a limiting reactant. So you're going to run out of whatever the smaller number of moles is. And then figure out which pH is. So what was the volume of the acid? I didn't write that down. Does anybody know, or do we need to go back for a second? Maybe we'll go back for a second. Okay, so the volume of our acid was 50 milliliters. I'll leave that up there for a minute. All right, so let's take a look at what we have. We wrote the reaction already. Okay, our hydroxide is reacting with the acetic acid. We're producing water and acetate. We're going to take the molarity times the volume of our base. That'll give us the moles of base. We're going to take the molarity times the volume of our acid. That'll give us the moles of our acid. And then we want to look to find out what our limiting reactant is. The hydroxide is our limiting reactant. And it reacts in a 1:1:1 ratio. So we're going to end up with 0.00500 moles of acetic acid and 0.00500 moles of acetate. This is a buffer solution. We can use the Henderson-Hasselbalch to calculate the pH. So the negative log of our Ka plus the log of our base over our acid, the base and acid are equal. The log of 1 equals 0, pH equals pKa. We're at the half equivalence point. So our pH is 4.745. Okay, how did we do with that? All right, so the next thing we're going to do is we're going to change this number. Okay, it was 50 milliliters. Now it's going to be 100 milliliters. Okay, you're going to be at, oh, I'm not going to say it yet. So change this to 100 milliliters and do the same kind of problems. See what you end up with. I'll give you a hint. It's not going to be a buffer solution anymore. And calculate your pH. Yep.
Are we adding 100 milliliters of acid or 100 milliliters of base for point C?
For C, we now have 100 milliliters of base.
Okay.
Yep. I switched it from what we did yesterday to what we did today. So we're adding base today. We added acid yesterday. Okay, we good with that? I'll go back to the question again so you can take a look at it while we work it out. All right, there's your question again. So again, this is our acid. That doesn't change. We're adding base. So 50 milliliters, now we're up to 100 milliliters. Okay, I'll give you a hint on this one. You have to write a KB expression. All right, so let's see how we did. This was a longer problem. The last one will not be as long. All right, so the hydroxide is going to react with the acetic acid. We're going to produce water and acetate. Okay, same reaction we had before. We're going to take the molarity times the new volume to figure out the number of moles of our base. We calculated the number of moles of acid, and that's not changing in the problem. We're actually now at the equivalence point for our strong acid, strong base. It reacts in a 1-to-1 ratio. We're actually going to produce 0.0100 moles of acetate ion. But we can't figure out the pH directly from the acetate ion. So what we're going to do is calculate the concentration of the acetate ion. And since the acetate ion is a base, we're going to do a weak base problem. So we've got our acetate reacting with the water. We're producing acetic acid and hydroxide. Once we calculate hydroxide, we're going to be able to figure out the pH of the solution. So we write our KB expression. We take the KW and divide it by KA to get KB. That'll equal X squared over 0.0667. Multiply both sides by 0.0667. Take the square root of both sides, and that's going to give us the hydroxide ion. Take the negative log of that. That'll give us the POH. Subtract it from 14, that'll give us our pH. That's a 5. Okay, so at the equivalence point, we're going to be left with weak base in the solution. We're going to do a KB expression to calculate hydroxide. And then from hydroxide, we can calculate the pH. Now, the last step is an easier step, okay? Because now the hydroxide becomes the limiting reactant. So I'm going to go back to the question. We're going to do point D and then see how we do with this one. Reaction's the same, just the numbers are different. Now we're past the equivalence point, so the hydroxide is going to be in excess this time. All right. Let's see how we did. All right, so our reaction is going to be the same. We've got the molarity times the volume of our base. So now we've got 0.0150 moles of base and that same 0.0100 moles of acid. So this time our acid is completely consumed. We're past the equivalence point and we're going to have extra hydroxide in the solution with no acid to react with. Now we do have this weak base in the solution as well, but we're not going to get a significant amount of hydroxide from here as we are from here. So we're going to take the moles of the hydroxide, divide it by the total volume. That gives us the molarity of the hydroxide. We can calculate the pOH, and then we can subtract it from 14 and figure out the pH. So our pH started out low because we had a weak acid in solution. We added a little bit of base and we were in the buffer region. We added some more and we were at the equivalence point, and this last step we're beyond our equivalence point. Okay, so hopefully doing a couple more problems of titration, we've kind of solidified what we need to do there. So it is just about 7 o'clock. Okay, I'm going to give you maybe 3 minutes break. Okay, get up and stretch for, just a couple of minutes. And then we're going to finish up our electrochemistry. Okay, so get up, take a break, stretch, go to the bathroom, whatever you need to do. And then we're going to come back and wrap up the content for the course. All right, so let's continue where we left off yesterday. So we started talking about redox reactions and electrochemical cells. And we said that we can write kind of shorthand cell notations for a particular reaction. So we're given this cell notation. We want to determine what's being oxidized, what's being reduced, what's the oxidizing agent, and what's the reducing agent. Okay, so the substance that's oxidized is going to be losing electrons, and the oxidation number or the oxidation state is going to be going up. So magnesium going to magnesium ions, or copper ions going to copper atoms. Which one is being oxidized? Magnesium or copper ions? Put it into the chat. The substance that's oxidized has an increase in its oxidation number. All right, so let's look. What's the oxidation number on magnesium here? Put that in the chat. Good, it's 0. What's the oxidation number on our magnesium ion? +2. So is the oxidation number going up or down for magnesium? Up, right? Okay. What's the oxidation state on our copper ion? What's the oxidation state on copper? 0. So is the oxidation state on copper going up or down? All right. So is magnesium being oxidized or reduced since its number is going up? Being oxidized, right? Okay. Copper is going from a +2 to a 0. The number's going down. That means it's being reduced. Okay. So magnesium is being oxidized because it's losing electrons. Copper is being reduced because it's gaining electrons. Now, we actually didn't talk about the terms oxidizing agent and reducing agent yesterday. So the substance that's oxidized is losing electrons. And when it loses electrons, those electrons are going to cause something else to be reduced. So the substance that's oxidized is the reducing agent. Okay. The substance that's reduced is gaining electrons, which means it's causing the other substance to lose electrons. It's causing the other substance to be oxidized. So the substance that's reduced is the oxidizing agent. They're just opposites. So since magnesium is being oxidized in this example, it's the reducing agent. I think I actually wrote that down somewhere. Since magnesium is being oxidized, it's the reducing agent. And since copper is being reduced, it's the oxidizing agent. Okay, they're just opposites. The substance that's oxidized is the reducing agent. The substance that's reduced is the oxidizing agent. All right, so let's look at these examples. Okay, we want to write the following balanced reactions in their cell notation, in their shorthand notation. So the oxidation comes first and the reduction comes second in our cell notation. So look at this reaction. Silver ions or copper atoms, which are being oxidized? Which one has the oxidation number going up? Silver ions or copper atoms? Right, silver ions. Silver ions are going from a +1 on the reactant side to a 0 on the product side. That means silver ions are being oxidized. Okay, sorry, they're being reduced. I'm doing this backwards, sorry. +1 to 0, silver ions are being reduced. Okay, the copper is going from a 0 to a +2. That means the copper is being oxidized. The oxidation comes first in the cell notation. So our cell notation would be the copper atoms going to copper ions. Okay, this is showing the oxidation half reaction. And then the silver ions are going to silver atoms. This shorthands the reduction half reaction. And this double line here essentially means that the oxidation is taking place in one compartment, which we said is the anode compartment. And the reduction is taking place in the other compartment, which we said was the cathode compartment. So using this A as an example, let's look at B. First, the nitrate's a spectator ion, so don't worry about the nitrate here and here. Okay, we've got manganese going from atoms to ions, and the charge on the magnesium is a +2 here. So it's going from a 0 to a +2. Think about what that means for the manganese in this redox reaction. The tin is going from a +2 charge to a 0. Think about what that's doing to the tin in this redox reaction. And then write your cell notation. Remember that the oxidation comes first in your cell notation, followed by your reduction. All right, so we've got manganese atoms going to manganese ions. Here's our oxidation. This is what's taking place in the anode compartment. We've got the tin ions going to tin atoms for our reduction side of our cell notation. And this is what would happen in the cathode compartment. So this is our shorthand cell notation for this reaction. All right. So now let's talk about these galvanic cells and spontaneity. When we talk about galvanic cells, sometimes they're called voltaic cells. They take place spontaneously, but we need to decide which direction is the spontaneous reaction taking place. So what we use are what are called standard reduction potential values to help us to decide which way the reaction is favored. Is it favored in the forward direction or towards the right? Or is it favored in the reverse direction towards the left? So what we have here is kind of a short abbreviated activity series or a reduction potential table. So it lists various substances and they're gaining electrons. So these are all written as reduction half reactions. And we're given the potential for this reaction to take place. Now, the more positive the number is, the stronger the oxidizing agent, or the more likely it is to be reduced. The more negative the number is, the stronger the reducing agent, or the more likely it is to be oxidized. And we're going to use that information to decide whether or not a reaction is spontaneous or not. So the potentials for the half reactions are measured in volts. Okay, so the V here are the units that we're using for our standard reduction potential values. And they're all relative to a hydrogen gas electrode, which we're going to look at in a second. And if the voltage is a positive value, the reaction is going to be spontaneous. Okay, so before we go through whether it's spontaneous or not, let's just do a little bit of a talk on electricity. So when we talk about cell potential, okay, the symbol that we use for cell potential is a capital E. The units are volts, which is a capital V. And it's essentially a measure of the difference of the electrical potentials between the oxidation half reaction and the reduction half reaction. When we use the term current, the symbol that we have for current is a capital I. The units are amps, which is a capital A. And it's a measure of the flow of electrons through a wire. And when we talk about resistance, the symbol for resistance is a capital R. And the units are ohms, this is a Greek unit for that. And it measures the resistance, the impediment of the flow of electrons. Okay, so to kind of summarize this up, this is just an example. It's not talking about electrons, but maybe it'll make more sense. Okay, if we have a cup filled with water, and let's say we have it filled to here, and we have a hole, okay, a little bit of the water is going to flow through that hole. If we have our cup of water and it's filled to here, we're going to have more water flowing out of that hole. The difference in the height is the difference in the pressure that causes the water to flow out of this hole. Okay, that's kind of like what we mean when we talk about voltage or our electrical potential. The difference between this value here and this value here. The current is kind of like the flow of the water out of this hole. Okay, the more water that flows out of the hole, the larger the current. The less water that flows through this hole, the lower the current. It's the same thing as if we talk about the flow of electrons through a wire. If a lot of electrons are flowing through a wire, it's going to be a high current. If a little bit of electrons are flowing through that wire, it's going to be a lower current. And then if this diameter of this hole is really small, there's going to be a great degree of resistance for water flowing through it. If the hole is really big, there isn't going to be as much resistance for the water flowing through it. Resistance is just the push against the flow of electrons. So the cell potential is measured in volts, and it has to do with the electrical potential difference between the reduction and the oxidation half reaction. The current is the flow of the electrons through a wire, and the resistance measures anything that acts in opposition to the flow of electrons. All right, now let's look at standard reduction potential values. When we look at the cell potential, it results from the difference in the electrical potentials between the two electrodes, the oxidation and the reduction. It's impossible to measure the value of electrical potential for just one electrode. So we measure it by a difference, a reference that we use as 0. And the electrode that was chosen as our reference electrode is the standard hydrogen electrode, which just stands for SHE. Okay, we have 1 ATM of hydrogen that's being bubbled through a 1 molar hydrochloric acid solution. So in this reaction, we're going to have the hydrogen ions gaining electrons and becoming hydrogen gas. And this has been assigned a reduction potential value of 0. Well, what do we use that for? Now, let's look at a voltaic cell. So over here, this is our standard hydrogen electrode. Over here, we have copper ions and copper metal. So this galvanic cell has our standard hydrogen electrode and our copper ion, copper metal half reaction. Okay, so when we look at the two half reactions that take place, in our anode, the hydrogen gas is becoming hydrogen ions and it's giving off 2 electrons. The electrons are going to flow through our circuit into our cathode compartment, where the copper ions are going to take in those electrons and become copper atoms. 2 electrons lost, 2 electrons gained. Here's our overall reaction. Now, this is the voltage that's read across this cell, okay, 0.337 volts. When we go to calculate the potential difference across this cell, we're going to take the value at the cathode and subtract the value at the anode. The reason why we're subtracting is because the values on the table are reduction values, but oxidation takes place at the anode compartment, and oxidation is the reverse of reduction. So looking at this equation, here's the measured voltage across this cell, 0.337. We don't know what the standard reduction potential would be here. So this is X. But by definition, the value here for the anode compartment is 0. And since we assigned this value as 0, we can figure out what the standard reduction potential is for this half reaction. So what that does is it enables us to come up with values. So I'm just showing you where these values come from. Okay, you're going to be given a table. So here's hydrogen, okay, relative to any of these half reactions here, or here's hydrogen relative to any of these reactions here. The reaction that takes place at the cathode is the reduction half reaction. And it'll be the reaction with the larger or less negative standard reduction potential. In the anode compartment, that's where our oxidation half reaction takes place. And that will be the half reaction with the smaller or the more negative standard reduction potential value off the table. So let's apply this. Okay, now that we've gone through kind of, what it all means, let's apply it in some questions. So let's say that we're looking at a standard potential, okay, which is at 25 degrees Celsius, 1 molar solutions, and 1 ATM if we're looking at gases. A spontaneous cell, a galvanic cell or a voltaic cell, will always have a positive voltage. So let's look at this example. Let's say that we have copper atoms reacting with lead ions to form copper ions and lead atoms. Well, the copper is going from copper atoms to copper ions. It's being oxidized. If we look this reaction up on the table, okay, we'd actually be looking up the reverse on the table because the table is always going to be a reduction potential value. We get 0.34 volts. Okay, we just looked that up on a table. If we look up the lead 2 ions going to lead atoms, the table tells us it's negative 0.13 volts. This number here, the 0.34, and this number here, the negative 0.13, these come off the table. It's the reduction potential value for copper ions going to copper atoms. And the negative 0.13 is the lead ions going to lead atoms. All right, to calculate the voltage across this cell, we would take the reduction potential at the cathode and subtract the reduction potential at the anode. Reduction takes place at the cathode, and lead ions are being reduced in this reaction. So for our E for our cathode, we're going to put in negative 0.13. Oxidation takes place at the anode. The copper atoms are being oxidized in this reaction. So we're going to substitute in for our anode negative 0.34. So we've got our reduction value minus our oxidation value, or what takes place at the cathode minus what takes place at the anode, and we get a negative 0.47. The important part is this negative sign. When we look at any type of redox reaction, it will only be spontaneous if the reduction potential value is positive. Since this value is negative, this reaction as written is not spontaneous. It's not going to take place on its own. So let's look at another example. Okay, let's say that we've got magnesium metal reacting with nickel ions, and we want to decide whether this reaction is spontaneous. Okay, well, the reaction at the cathode, which is the reduction half reaction, is going to have the larger reduction potential value. And the reaction that takes place at the anode, which is the oxidation half reaction, would be the one that has the smaller reduction potential value on the table. So this is the information we get on the table. You would just look it up. Okay, you'd look up magnesium to magnesium ions on the table, and the value on the table is negative 0.2372 volts. We look up nickel 2 ions to nickel atoms on the table, and we get negative 0.257. All right, now to calculate the cell potential, we would take the reduction value that takes place at the cathode and subtract the oxidation value that takes place at the anode. So at the cathode, we've got negative 0.57 or 257. We'll plug that in here. We're going to subtract the value that takes place at the anode, or the oxidation, which is negative 0.2372. Okay, subtracting a negative is the same as adding a positive. We end up with a positive voltage difference across this cell. That means this reaction is spontaneous. So magnesium being oxidized and copper ions being reduced will take place spontaneously. As long as the reduction potential difference is a positive value, the reaction is spontaneous. If the value is a negative value, it's non-spontaneous. So let's look at another reaction. Okay, the nitrates are all spectator ions. Iron is going from a +2 charge to a +3 charge. So iron is being oxidized. That's what's going to take place in the anode compartment. The gold is going from a +3 charge to a 0 charge. So the gold is being reduced in this reaction, and that's what would take place at the cathode compartment. We want to decide whether or not this reaction takes place. And again, what takes place at the cathode compartment is the reduction half reaction. So it would be the one with the larger reduction potential value. What takes place in the anode compartment is the oxidation, and it would have the smaller or the less negative, or sorry, more negative reduction potential table. This is what we get when we look on the table. Okay. The iron is being oxidized. That's what's taking place at the anode. The table tells us 0.771. The gold is being reduced. The table tells us that's a 1.498. So take the cathode value, subtract the anode value, decide whether we get a positive or a negative value for our reduction potential difference, and decide whether this reaction in the direction it's written is spontaneous. It's the cathode value, subtract the anode value. All right, so 1.498 is our cathode value. 0.771 is our anode value. So 1.498 minus 0.771 gives us a positive value. That means this reaction is spontaneous. So what you would need to do to decide whether a reaction you're given is a spontaneous reaction or not is you need to decide what's being oxidized, look up the value on the table, what's being reduced, look up the value on the table, take the reduction minus the oxidation. If the value is positive, it is spontaneous. If the value is negative, it's non-spontaneous. Now, let's connect this to equilibrium, which is what we talked about in the last couple of chapters. So when we look at galvanic cells, they take chemical energy in that redox reaction and they convert it to electrical energy. And the electrical energy can do work. So that gives us an equation. Okay, the electrical work that can be done by a galvanic cell equals the potential difference between the reduction and the oxidation times the charge, and the charge is in terms of coulombs. Now, the charge of 1 electron equals 1.602 times 10 to the minus 19 coulombs. This is a constant. And if we wanted the charge for a mole of electrons, because we usually don't talk about things in terms of 1 electron, it's usually a mole of electrons. We can convert a mole of electrons to electrons, knowing that Avogadro's number of electrons equals 1 mole. And then we can convert electrons to charge. So 1 mole of electrons is equal to 9.65 times 10 to the 4 coulombs per mole of electrons. And this constant has a name. Okay, it's called Faraday's constant. 9.65 times 10 to the 4 coulombs. All right, so we're going to look at an equation here that relates work to our reduction potential. So the W in that equation stands for the electrical work. N stands for the number of moles of electrons in that system. F stands for Faraday's constant in terms of coulombs per mole of electrons. And our E cell is our cell potential. The negative sign here is there because the system, the galvanic cell, is doing work on the surroundings. Now, to relate that to our free energy value or our G value, okay, the free energy is the energy that's available to do work. So what we can essentially do is substitute in delta G for W. So this is the equation that we would work with to relate free energy to our potential difference. If delta G is less than 1, if delta G is a negative value, we know that that means it's a spontaneous process. We learned that in a previous chapter. And if delta E for our cell, if our reduction potential value for our cell is positive, we know that the process is going to be a spontaneous process. So delta G equals negative NFE. This is a new equation. Delta G also equals negative RT ln of K. This is an old equation that relates free energy to equilibrium. We can set these two equations equal to each other. Since we've got delta G here and we've got delta G here, this value equals this value. Now, if we want to calculate just the potential difference, we would just divide both sides by negative NF, and that gives us a new equation. And this new equation has lots of constants in it. Okay, we've got R, which is a constant. We've got T, which is, if we're at standard conditions, is 25 degrees Celsius or 298 Kelvin. And we've got Faraday's constant, which is a constant. So 8.314 times 298.15 divided by 9.65 times 10 to the 4th can be summarized in a constant, 0.0257 volts. It's just taking the three constants and putting them together in one constant. So we can summarize this by saying that the voltage across a cell equals 0.0257 divided by N, that's the number of moles of electrons, times ln of K. We can also convert that. Instead of using ln, we could use our log, and we've got 0.0592 divided by N times the log of K. So whether we want to use the ln value or we want to use the log value will give us a little bit of a different equation. So this relates everything here. We've got delta G, that's our free energy, and we've got K, that's our equilibrium constant. And we already looked at this equation here. So delta G equals negative RT ln of K. Now we're just going to add in this new variable, our potential difference. Okay, so if we want to relate our free energy to E, we've got negative NF times E equals delta G. And if we want to relate E to K, E equals RT over NF times the ln of K. Now, a reaction is spontaneous if K is bigger than 1, so we have more product than reactant. Our free energy is a negative value, delta G is a negative value, and our potential difference is a positive value. A reaction is non-spontaneous if K is less than 1, so reactants are bigger than products. Delta G is a positive value, or our voltage is a negative value. And the reaction's at equilibrium if K equals 1, delta G equals 0, and E equals 0. So let's look at a problem. Okay, we're given tin atoms reacting with copper ions to form tin ions and copper atoms. We look up on the table the value for the oxidation, negative 0.134 or 138, the value for the reduction, 0.153. So step number 1, calculate the potential difference between the reduction and the oxidation. So you're taking the cathode value and subtracting the anode value and see what you get for the voltage across our cell. So the cathode is 0.153. The anode is 0.138. So 0.153 minus negative 0.138 gives us positive 0.291. All right, next thing we want to calculate. What's the free energy? We're going to take negative N times F times E for our cell. The N is the number of electrons. So in this case, 2 electrons are being lost in our oxidation, 2 electrons are being gained in our reduction, so N equals 2. F is Faraday's constant. E, we just calculated here, 0.291. So we've got negative 2 times 9.65 times 10 to the 4th coulombs per mole of electrons times 0.291. Again, we calculated the 0.291 here. This value is Faraday's constant, so it's always going to be this number. And the 2 is the moles of electrons that are being transferred between our oxidation and our reduction. So delta G is 56,200 joules per mole of electrons, or negative there should be a negative sign here, negative 56.2 kilojoules per mole. Now that we know delta G and we know E, we can calculate K. We're going to multiply both sides by 0.0257 and divide both sides by 0.0257, multiply both sides by N, And that'll leave us with ln of K. So the ln of K equals E times N over 0.0257. Now, we don't want the ln of K, we just want K. And if you look on your calculator and you find the ln button, the second function of that is the e to the x button. So K equals E to the E times N divided by 0.0257. So K equals 6.83 times 10 to the 9. All right, so to look at the numbers, E is 0.291. Delta G is negative 56.2, and K is 6.83 times 10 to the 9th. Okay, that means E is greater than 0. Delta G is less than 0. And K is bigger than 1. That means this reaction is spontaneous under standard conditions. Again, standard conditions being 1 molar concentrations, 25 degrees Celsius, and if we were talking about gases, 1 atm for gases. There are no gases in this one. All right. So what if we're not at standard conditions? Because often things are not at standard conditions. Well, now we have a little bit of a different equation, which we looked at in a couple of chapters ago. So if we were to look at our free energy at non-standard conditions, it equals our free energy at standard conditions. That's what this little 0 stands for. Plus RT ln of Q, that means we're not at equilibrium. So we can substitute in for delta G, negative NFE, not at standard conditions. We can substitute in for delta G naught, negative NFE at standard conditions, plus RT ln of Q. So we're going to do a little manipulating with this equation. We're going to divide everything by negative NF. That cancels negative NF out on the left-hand side. It cancels negative NF here, and we're just left with E naught. And we're going to be dividing this by negative NF. So we get negative RT divided by NF ln of Q. And again, R is a constant, T is a constant, F is a constant. So we can just put all those constants together and come up with a new constant. And this equation is called our Nernst equation. So the voltage in a non-standard cell would equal the voltage in the standard cell minus 0.0257 divided by N times ln of Q. Or just a slightly different version would be 0.0592 divided by N times the log of Q. There's just a different function. This is a log function. This is an ln function. It doesn't matter which one you use. And this is called the Nernst equation. So let's look at an example. This is a non-standard cell. How do we know that? Well, standard cells are 1 molar. This is only 0.15. And this is only 0.0025. So this is a non-standard cell. The aluminum is going from atoms to ions. So it's being oxidized. That would take place at the anode. We can look up the value on the table for aluminum, and it's negative 1.662. This comes off the reduction potential table. The copper ions are being reduced. Reduction takes place at the cathode compartment. And when we look that up on our reduction potential table, it's 0.34. So if we take the cathode value and subtract the anode value, 0.34 minus negative 1.662 gives us 2.00. Okay, that's the voltage across our cell. For Q, we would take our products over our reactants. So 0.15 squared over 0.025 cubed gives us 1,440 for our Q value. Now we can calculate the voltage across this non-standard cell. We would plug in the voltage if the cell was at standard conditions, which is 2.00. We would substitute in 6 for N because 6 electrons are being lost and 6 electrons are being gained in this equation. And we'd substitute in 1,440 for Q. And when we plug that in, the voltage across our cell is now 1.98. Okay, so let's look at that for a second. If the concentration of aluminum ions was 1 and the concentration of copper ions was 1, this would be a standard cell. And if this were a standard cell, the voltage across that cell would be 2.00 volts. But we're not at standard conditions. The molarities are not 1 molar. So the voltage across this cell would be less than what it was under standard conditions. That's what we mean when we talk about our Nernst equation. All right, batteries. We're going to go through this super quick. When we talk about batteries, batteries are electrochemical cells. Okay, they take chemical energy and convert it to electrical energy. They're essentially a galvanic cell. Okay, there are 2 types of batteries. There are primary batteries. Okay, those are ones that are one and done. Okay, you can't recharge a primary battery. A secondary battery is a battery that can be recharged. You use up the energy that was in that cell, and then you recharge it again. And that's as far as we're going to go for batteries. We're not going to go into any more detail on that. Okay, when we talk about corrosion, okay, corrosion is another type of redox reaction. Again, it's an electrochemical process. So to give you an example, okay, here we have some iron. And typically iron is coated with something so that it can't rust. Maybe it's painted with a layer of paint that enables the iron to not be exposed to oxygen and water. But if some of that paint is chipped away, the oxygen is going to go through a reduction reaction. The iron is going to go through an oxidation reaction. The iron ions will then react with the water and produce rust, iron oxide. And that's a positive voltage, which tells us that this process is a spontaneous process. Iron corrodes spontaneously. It's an example of a redox reaction. Okay, the last thing we need to do is talk about electrolysis. So electrolysis is a process that causes a non-spontaneous reaction, a reaction that's reactant favored to occur. And the way that electrolysis takes place is we force the electrochemical cell to work in the reverse direction, in the non-spontaneous direction, by adding in an external energy source. Okay, it's used in purifying metals. It's used in electroplating. So if we were to look here, here's an example of an electrolysis process where we're going to be turning chloride ions into chlorine gas and sodium ions into sodium metal. We need an electrical source, an outside source, in order for this process to take place. And we don't have any salt bridge when we look at these electrolysis processes. So in this case, the chloride ions are being oxidized into chlorine gas, and we're generating electrons. The sodium ions are accepting those electrons to become sodium atoms, and we're producing sodium atoms, liquid sodium, and we're producing gaseous chlorine. Electroplating. Okay, let's say that we have a solution of silver nitrate, and we put in a silver electrode, and we put in some spoon. If we add in an electrical source, we're going to electroplate this spoon with silver. What would happen is the silver metal in our anode would lose electrons and become silver ions in the solution. The electrons would flow over to our spoon. The silver ions in the solution will absorb those electrons and become silver atoms, and the silver atoms will plate onto the spoon. The mass of the silver electrode here would go down over time as the silver atoms are becoming silver ions. And the mass of this spoon would go up over time as the silver ions become silver atoms and plate this spoon. So math-wise, if we were to look at silver ions becoming silver atoms, it's a 1-to-1 ratio with respect to the silver ions and the electrons. If we were to look at something like copper ions to electrons, the ratio is a 1-to-2 ratio. Matter and charge are conserved in chemical reactions. And when we look at these balanced equations, we're going to be able to use the stoichiometry in those balanced equations to figure out how much metal we can plate out in our electroplating process. So the number of moles of electrons transferred during a redox reaction is determined by the flow of electrons in that external circuit. So a couple of equations. Charge equals current times time. Current is I, time is T, charge is Q. When we talk about a coulomb is defined as 1 amp times 1 second, means the same thing. And charge is converted to moles of electrons with Faraday's constant. So this was written before as 9.65 times 10 to the fourth. This time it's just written out as 96,500 coulombs. It can be written either way. Equals 1 mole of electrons. So let's put all of that together, and it's going to look like a stoichiometry problem. What mass of nickel will be deposited on the cathode of an electrolysis cell if a current of 20 milliamps for 1 hour flows through an aqueous solution containing nickel ions? All right, first of all, the nickel ions are going to absorb electrons and become nickel atoms. And the ratio is a 1 to 2 ratio. That's going to be important. And we know that our charge equals our current times our time. The current is 20 milliamps. Well, we can convert milliamps to amps the same way we could convert like milliliters to liters. Okay, 1 milliamp equals 10 to the minus 3 amps. So here's our current in amps. We multiply it by our time in seconds. 1 hour equals 3,600 seconds. So our charge is 72 coulombs. All right, so now we're going to do a little stoichiometry. We can take 72 coulombs and use Faraday's constant to convert from coulombs of charge to moles of electrons. This balanced equation here enables us to go from moles of electrons to moles of nickel. And then the periodic table enables us to go from moles of nickel to grams of nickel. So if we were to pass 20 milliamps for 1 hour through a nickel ion solution, we would electroplate 0.022 grams of nickel onto the cathode. So that's as far as we're going to go for today. I want to remind you of a couple of things. You have a test tomorrow. Okay, the test will be open at 11. It will close at 8, same as all of your other tests. Remember that I did send in an email a formula sheet, which you can use on your test. It does have Ka values and Kb values, which will be helpful on your test. So I would suggest you either have that open on your computer or you print it before your test. It'll make it a little bit easier. We have class on Thursday. We will go through another electroplating problem. We'll do a couple of problems in our warm-up as well. And then we're going to spend the rest of the period reviewing for your final exam. Okay, the final exam is part chapter on KSP and the chapter on electrochemistry. That's 60% of your final exam. And then part will be a review of all the other chapters that we covered during the semester, and that'll be 40%. Okay, and we'll talk about that in a lot more detail on Thursday. If you finish all of the labs that are remaining, the lab that's due Friday, the lab that's due Monday, and your extra credit lab, if you have those 3 labs done by Thursday at 11:59 p.m., I'm going to add an additional 10 extra credit points to your lowest test grade. Okay. If you choose to just do your test or your lab that's due on Friday, that's fine. If you do the lab that's due on Monday and your extra credit lab that's due by Monday, by Sunday night, I'll give you 5 extra credit points. And then if you wait until Monday to finish those 2 labs, you won't get any extra credit points on top of the extra credit points you would just get for doing that extra lab. Okay, Monday is your final exam. Again, it's going to be open from 11 in the morning until 8 at night. And we'll talk about a lot more detail about your final exam on Thursday. We will spend most of the time on Thursday reviewing. If there are specific things that you want to review, please email me and I'll make sure that I include it in the review for Thursday. And there were a couple of questions. So we have 3 labs left. So you have 2 labs and an extra credit lab. So yeah, you have, if you count the extra credit lab, there are 3 labs left. 1 due Friday, 1 due Monday, and your extra credit lab due Monday. If you can get them done ahead of time, I'm going to give you extra credit for getting them done in advance. The final exam is going to be the same time length as the other tests are going to be. It's not going to be any longer than your previous tests. So it'll look very similar. The content, will be different, but it'll be very similar. All right. So let me stop